Okay, today we have a very special guest. It's the president of the Radio Amateur Satellite Corporation of North America, Joe Spier. Joe.
Short and sweet. All right, do I really need this, or I guess it's for the microphone, Greg. Okay. All right, I'm not going to stand behind this because basically I like to wander around a little bit, and I wore for you guys, especially my space socks. So you should be able to see a little American standing on the moon. No one else has done that yet, I believe, although the Chinese recently launched a couple of satellites that are in lunar orbit that they asked to give Oscar numbers, and we granted those to them. So a lot of people ask, what's AMSAT? It is the Amateur Satellite, Radio Amateur Satellite Corporation. And we have been doing this for almost 50 years. AMSAT incorporated in 1969, and I'm going to have to ask someone to hit enter there to change the slides, or I'll be running back and forth like a crazy man, which is also what I do. So AMSAT's a nonprofit. We raise money to build these satellites by taking donations. And what currently is a satellite? This is a Fox satellite. So AO91, AO92, AO85 are all this size. This is called a 1U, or 10 centimeter, 10 centimeter, 10 centimeter cube, 1.2 kilograms. And I'll pass this around. It has bare boards in it. So if we populate this board and put some solar panels on it, we could probably launch it if we could find somebody to pay for that. So it has a camera on it like AO92 does, and this last week we were trying to turn the camera on as it was over the East Coast to get some imagery of the hurricane that was coming ashore over the East Coast. So I'm not sure how successful we were yet. I haven't seen any full pictures of the hurricane yet, and since it just came ashore this morning, I'm not sure we've got them yet, but we actually stitched the digital images together to create one frame. And it's only VGA, but it still requires a license. So I'll go ahead and pass this around. You guys can look at that. Make sure I get that back. That is not a door prize. Darn it. So we're a bunch of licensed space enthusiasts, I guess is the way you could say about this. I remember when Aerojet fired the second stage booster down there in Rancho Cordova in the mid-60s. And I got to hear it from North Highlands, 26 miles away, which I also think is probably Ted Nugent's record for noise complaints at the St. Louis Checkerdome anyway. So we do technical research and development. We are about learning how to operate amateur radio in space. And we have one paid employee, Martha, who's been with us for 40 years, and she works in the office in Maryland. So basically there's 15 other groups around the world. This next month I'll be speaking in England at the AMSAT UK colloquium. I think in Milton Keynes or something like that is the name of the place. It's near Bletchley Park. And that'll be the first time in probably 20 years that the president of AMSAT US, AMSAT UK, and AMSAT DL will all be at the same place at one time. So we're having a mini little satellite summit at the bar. So we'll try to come up with what we're going to talk about at that point. So like I said, our 50th anniversary, the first satellite launch was Oscar 1, which Lance Jenner launched back in the early 60s. And Project Oscar sort of preceded AMSAT through the 60s up to Oscar 2, Oscar 3, and Oscar 4. By the time Oscar 5 came around in 1969, AMSAT had been formed, and it was kind of a group that came together as the East Coast sort of Project Oscar. Project Oscar still exists, but it's just not as active as it used to be, and AMSAT is the main priority, the main sort of satellite functionary for the US and North America. That includes Canada and Mexico. Okay, so hit that again. So we design, we have partnerships, we do partners with universities. We also do a thing called ARIS, Amateur Radio on the International Space Station. And that allows school kids to have about a 10-minute contact with an astronaut on the space station. They get to ask a question of an astronaut. So this is to key interest into STEM education. And we do, scientific innovation. Part of our satellites that are up there right now, we're actually doing L-band uplinks, which is our own experiment on the satellite. Nobody paid for that but us. So we deploy satellite systems. Right now it's LEO. We had AO-40, which was a satellite launch about 2000. It was almost the death knell of AMSAT after a valve was left open, and it sort of renated in space, to use the term, was no longer nominal. So we've had a few satellites that have had sub-oceanic orbits. Not our particular fault. The rocket that was carrying it went that way. So we don't pay for insurance. We pay to build the satellites, and then we sort of cajole people into launching them for us. Nowadays, NASA has a program called the CubeSat Launch Initiative, which is CLAI, or a CLI program, and then you get a ELANA number, which is the Educational Launch of Nanosatellites, once you get the grant. That grant is good for about $300,000 of launch cost. You have more mass, or you have a higher orbit requirement, or something like that, you pay the balance. And all of these funds that AMSAT uses come from the amateur radio community, or come from fundraisers that we do around anywhere. So it's all tax-deductible donations. That's how we fund our hobby, amateur radio in space. So I need a clicker. Basically, this is it. What we do is we try to keep amateur radio in space. So hit it again. Here's my shameless plug. We arrange this year, we have a symposium every year, which we get together and we publish our proceedings. We have to publish things so we don't violate ITAR, the International Treaty on Arms Reduction. And that way, when we talk about something, we can talk about it in the public domain without having to keep things quiet. Like for this year, a lot of things we're working on, I can't tell you about it because it's not published yet. So we can't tell you what we're doing other than, yes, we're working on that. So one of the things that I can say that we're working on is our golf series project, which this is a 1U CubeSat that's going around. Golf is 3U. So it's like 3 of those stacked on end. It's about the size of a shoebox and weighs 3 kilograms. We're working on what's called an altitude determination and control module. Basically, it is station keeping. And that's about all I can say about that. So our symposium this year will be in Huntsville, Alabama at the U.S. Space and Rocket Center, and our banquet will be underneath the Saturn V. If you'd fancy a trip to Alabama in November, come join us. I'd love to have you there. I'll be there running amok because we have a 2-day board meeting right before the symposium, so the president is the last person you want to talk to at a symposium. Okay, go ahead and hit the next one, Greg. So basically, let's talk about satellites. So there's different orbits. And what's an orbit? Well, the moon's in an orbit, so that's a lunar orbit. And we have satellites up there. People are kind of familiar with satellites. We have LEO, low Earth orbit. So who knows how fast you have to be to achieve an orbit? How fast in miles per hour? Yeah, go ahead. This is 20 questions.
About 5 miles per second.
5 miles per second. You're going to do the math to get it up to miles per hour? Or
Let's see, 17,500, yeah.
Good math. We could use you in AMSAT. Math is an important key. So that's my pitch for STEM out there. Learn math. And I have found that math is a preventative for Alzheimer's. So if you make change in your head all the time and do calculations, you're probably going to last a good long life. Then we have our GPS satellites are up around 4,000 or 5,000 kilometers. The others are up to 300 kilometers. That's where the ISS is. We run around about 17,500 to stay in orbit, and it is a slowly decaying orbit. So a lot of our re-entry plans are, it burns up. Sometimes after 6 years, sometimes after 20 years. So we like longer orbits. We like to have batteries last a long, long time, so we get to use our basically transponder in the sky for a long, long time. And then when you get out to your geosynchronous orbits, and Molniya, I had to look that up, in Russian orbit, they are elliptical, and you will never get another one of those orbits because it crosses the geostationary orbits where billion-dollar satellites are, and you will no chance of running into one of those. So that is basically what the orbits are. You're way high, 23,000 miles almost for the HEO orbits or the geosynchronous orbits. And geosynchronous stays in one place, so it's actually moving at the same speed of the Earth, but then you've got to point it. So that's some of that station keeping that the big satellites use, and they have combustibles. So the combustibles are to keep it in orbit, and the real secret is, well, if we can go to GEO, what they do when they launch a GeoBird is they put it into a parking orbit that's up higher than the GEO orbit in the belt. So we don't really care about being in the belt. We could just hang out with all the junk. We've made our, our deorbit plan. We're there, and we can just operate with all the junk. So that's one of our kind of secret ideas we're looking at. Can we get up there with the junk? And if you think about it, what it gives you is a GEO orbit that about 2 weeks out of every month, you have a satellite overhead that drifts slowly across the horizon. So that's kind of been one of our dreams. We're trying to come up with new methods. Instead of spending $4 million to launch a satellite into GEO orbit, let's just ride up with the trash for about $600,000. So even though I say $600,000 like that's cheap, that's not. So hit the next one, please. So satellites come in all sizes, all shapes. Here's Oscar 1. There's a spacesuit. So every now and then, one of the Russian spacesuits comes available. We stick a radio in it and throw it overboard. Looks like a little man floating away. School kids like that. Some of these are huge. Here is AO-40. That thing's about the size of a VW. So that costs a lot more. Phase 3E, you've maybe heard about. AMSAT-NA built it. It is still in a closet in Germany. It is so big, so massive, nobody can afford to launch it in today's environment. So we use amateur radio frequencies that are set to satellite bands. It's about 200 kilohertz in VHF and UHF. And we have other frequencies that we use in higher bands. Right now we're trying to get 5 and 10 gigahertz utilized. So hit that again, please. So how satellites operate like repeaters. So have you used a repeater on a mountaintop? Come on, this is the audience participation part. You got to wait. Okay, you've used a repeater, right? I need to make that clear. So this is a crossband repeater. You transmit on UHF, it comes down on VHF. And it's also a crossband repeater that moves across the sky. So it's in a path across the sky. And in low Earth orbit, the path takes about 9 or 10 minutes to go from horizon to horizon. So that's what we're operating with, is a small satellite that moves very rapidly across the sky, and this enhances a little bit of the effect called the Doppler effect. And typically the Doppler effect, you only have to adjust on your transmitter. And you adjust about 10 kilohertz above, below as it's coming towards you, and then above as it goes away. So that's the Doppler effect you have, and you can program this in your handy-talkie on about 5 different memories. So about halfway or a quarter way through the pass, you just change the frequency, and you don't have to worry about the Doppler effect as much, and you can actually get into one of these satellites with a handy-talkie. So great location. You can see some of the footprints depending on the altitude of the satellite. You can have a footprint that could be the entire United States or the eastern seaboard in Europe, Hawaii, Alaska, and the West Coast. So there's great footprints, great ways to do DX, great ways if you're into contesting. You can collect all grid squares. Guys go out and work these grid squares. We'll climb mountains, go to the coast, wherever you can imagine a wild camping trip would be. They'll be out there with their GPS standing on an imaginary line. So go ahead. So currently there's about 14 satellites. The ISS packet, it came back to life. Have no idea why. We're sending another one up there anyway, but it did come back to life. We thought there might be a bad cable, and apparently something got jostled around, and the packet's working again. Keep your fingers crossed. In November there'll be a new module will go up, and it'll continue to work. So there's different types of repeaters. There's your standard crossband repeater. There's a digital store and forward repeater, and then we have what's called single sideband and CW linear transponders. So how do we track them? Well, we use software. And basically the software, you can choose which ones are going to be displayed. The ABCD, you choose your satellites there. This software will actually send the signals to your radio. It will do the Doppler for you. It'll send the signals to your azimuth and elevation rotors that will track the satellite for you. So you don't have to arm wave a Yagi antenna out there and get your arm tired or use a tripod or something of that nature. There's two ways of doing this. There's the automated way and there's the manual way. So this also does the antenna control, and the graphics will do real-time satellite graphics. So it's a way, this is how we track the orbital elements of the satellite, and developed by Johann Kepler back in the 1500s, the mathematics to actually follow orbital motion in space. So next one. So we also have an online pass prediction, so you can put your lat long in and see what's going to come up in the next day or so for different satellites. It shows you about 2 passes, gives you the elevation, the azimuths, to be able to track the satellites. You can go out there and arm wave with a Yagi if you want. And that's at AMSAT.org. So here's some of the satellites. This is one of the old ones, Saudi Sat, which we call SO50. And it is if you see this is the uplink, this is the downlink. So uplink is on VHF, or UHF, downlink is on VHF. You need a tone on it. So there's a tone to initialize it and a tone to talk to the satellite. And it changes. And if you look at the power of the transmitter, 1/4 of a watt, that's all this satellite has. So remember, this is direct line of sight, straight down at you.
I like your technique for unfurling the little whip antenna on there. And you've got to wound around, and I guess you put current through the component there, burn it.
Yes, we use Ohm's law.
Yeah.
And it's called a Berger Resistor, but actually it doesn't burn anything. What it does is it melts the fishing line and it elongates until the surface tension of the fishing line can't hold it anymore. And if you look on any of the AO92 images that we have, you will see the end of the antenna with the little piece of fishing line still attached.
Is that antenna that's on there the antenna?
That is a nickel chromium wire that is the actual material that we use to make the antenna.
There's no further connections to any ground.
Yeah, that's it. And like AO85, when I get to that slide, AO85 is a little hard of hearing. We're pretty sure that the antenna delaminated from the spacecraft, so that's why it takes a little more power to get into the receiver.
It's nice you guys put some ham and memory on the bottom of that.
Yeah, Tony was our vice president for engineering, and he passed away before we could get AO85 launched. So in his memory, we stuck his name on the cards before we ever built AO85 and got it launched 3 years ago.
Very nice.
So we do that. We also do, I'll get into the sales pitch. If you'd like to contribute to golf, we'll put your name on a little chip that goes to space, name and call sign. And I think Eris does the same sort of thing. If the more money you get, the more bennies. That's how amateur radio works, right? So AO7. So here's a great story. AO7, early in the AMSAT world, launched in '74. It died what happens is the batteries are what dies in these satellites. So battery life is real critical. And we had a former AMSAT president, Robin Harrington. He kept listening for AO7. He would listen on all the dead satellites to see if they were transmitting again, because, I don't know, he was bored, who knows. AO7 started making noise again. So what they think happened, and since this is a spacecraft and we can't go up and diagnose it, they think that the batteries shorted together back in the 80s. One of the cells shorted together, and that put all of the power that came in from the solar panels to the spacecraft frame. So it's basically dead short. Nothing works. After a while, the batteries in 2000, they opened up because of the environment that the spacecraft is in. So now it opens up, so the power from the solar panels is now going back to the spacecraft. So the spacecraft now works only when it's in sunlight. So we have a spacecraft that was launched in 1974. It is still operational today when it's in the sunlight. The problem is that the components are also from 1974, and they're a bit finicky. So if you use 20 watts and hit that receiver on the spacecraft, what you do is you're putting so much current through those aged components that it flips its mode, and it doesn't, you never know what mode it's going to come back up in. And we call this FMing, as in F and magic, the satellite. So if you're using the satellite, please use the appropriate amount of power, like a good amateur radio operator would, to not trip the satellite again. And that's why we say no FMing on it. So it's basically operating only off of the solar panels. And we call that zombie mode, because the zombies only show up, at night, and this only works during the day. So it turns into a zombie at night. And this is Jan King, the first president of AMSAT. I am the 10th president of AMSAT. So in 50 years, we've had 10 presidents. Jan King was the first one. That is him with Alpha Oscar 7 in the environmental chamber. We do shake and bake. We have to launch these satellites just like a real corporation. We put them in an oven. We heat them up to spacecraft temperatures. We shake these things to 26 G. And if it doesn't fly apart, then we integrate it for launch. If it does fly apart, we try to put it back together and integrate it for launch. So FunCube, AMSAT UK launched FunCube in 2013. This is what we call a linear satellite. And if you notice, it has a band, a 20 kilohertz band that it operates in. So you'll talk to it on an upper or lower sideband, and we have inverting and non-inverting satellites, and they're listed as to, you talk to it on lower, it comes back on upper, or you talk to it on upper and it comes back on upper. It just depends on where in the band or what the satellite builder decided to do with it. And it has a telemetry beacon, and they have what's called fitter messages, where it's kind of like Twitter. You can send a message up to the satellite and it sends the message back down, and the UK school kids, for some reason, go crazy over that. I don't know, maybe they're hoping to be president someday, who can tell. So next one, please. So FunCube was launched in November of 2013. It is again that same size that we're passing around. They make it available on weekends for amateur radio use. So they operate this as an educational satellite. That's how they got it launched from the EU. And basically they sold little USB dongles with receivers on it to raise money to build this satellite. Go. So we have a book that's called Getting Started, and we get a $25 donation for this. So go on the AMSAT website if you're looking into doing this. We talk about all the satellites that are out there, how it works, the software, what equipment to use, and the linear satellites, what type of ground station you can have, everything from a handheld with an elk or an arrow antenna, a Yagi directional antenna. We like to say use full duplex so you can hear yourself come down on the satellite to make sure that you're into the satellite itself and transmitting and receiving on the same frequencies as everybody else. And it's basically how to do it. It's a getting started guide. And I will say, use the guide if you're interested in operating satellites. Don't be like me, who the first thing I tried to do was build a complete automated ground station, which I was successful, but it was a lot harder than just using a handy-talkie. So that is just what it is. There's easy ones to operate up there. We had a dearth of FM satellites, and now we have 4, I believe. So there's SO50, there's AO85, AO91, AO92, and by the end of the year, there should be another FM satellite up there. I know the launch date, but you don't look trustworthy enough to know. It's scheduled to go up out of Vandenberg, I can tell you that much. And before the end of the year is the date. So hopefully along about symposium time, we should have another FM bird up there. And that one should have a camera on it as well. So go ahead and hit Greg. So here's what it costs. Let's look at this a little bit. We can all scream together. That little CubeSat I passed around, $100,000 to get that to low Earth orbit. If you want a 3U to low Earth, well, that's 3 times as much, 300K. If you want a microsat, which is about 20 pounds, that's $500,000. Aerosat, the one that we sent up a couple of years ago, we got a subsidy for that $1 million launch to the ISS. Basically, the Russians gave us a free ride. Smallsat to LEO, $3 million cost. And like a phase 3E to geotransfer orbit, notice I did not say geostationary, just to get it to the place where we can fire the rocket engine, $10 million. So if you're looking for donations and that kind of stuff to be able to give to a 501c3, 10 million will do it. I mean, I could really go for that, but we all realize that we're amateur radio operators and that we're a lot of small clubs, so we take whatever we can get and we try to get that to space. So that's what it takes. Like I said, if there's Elon Musk is hiding in the crowd here, come see me later. So this is why education becomes important to AMSAT.
I just wonder how many employees do you have?
1.
Well, I mean, the people working on this project.
AMSAT has 3,200 members, and they all think they're employees.
Oh.
And directors of the board.
At the laboratory, guys that actually build it.
The guys that actually build it, we probably have about 15 or 20 people working on the actual spacecraft at any time. And they are all over the United States.
Thank you.
Have people doing programming, people doing hardware, people doing integration, you name it. And we also have to farm some things out. But we cut good deals. So one of the good deals that we cut is education-wise. STEM is very important to our nation. It really is. I want kids that are smarter than me out there, so when I get to be an old codger, I'll let the gray fool you, that they can advance humankind. That's really what I want. I want the young folks out there to know more than me. Because I'm a big dummy and I stumbled along and made it this far, and I figured that they can make it a lot further if they get the education a lot sooner than I got it. And space excites kids. There's sort of 3, I call them the big 3. It's got to be space, it's got to be robotics, or it's got to have some sort of programming. Like Raspberry Pi, that sort of thing, where they can program things. And if you can combine a couple of these fun items for the youth of today, you've got a great, great thing going on. So space is a big thing, programming is a big thing, and the robotics, well, if you can get it to do something in space, you've got all 3. So we try to grab kids young with ARIS contacts. We try to get them interested in amateur radio to build satellites of the future. By the time they get to undergrad and college, they are building satellites. And we try to get them, to help them get them launched. And there's a lot of obstacles, the FCC being one of them, the International Amateur Radio Union being another. There's a lot of regulations we have to go through, and we try to assist them to get their launches. And then by the time they're in grad school, they're building, you know, satellites for SpaceX. We have a couple of folks that built experiments for AO-85. They work for SpaceX. And they won't help us now because they work for SpaceX. So we try to partner with these universities so we can get these CubeSat launch initiatives to get the free launches or the subsidized launches from NASA. And that's really our goal. We tried to build slots in those CubeSats to put experiments from universities. And we've been successful with Penn State Erie, with Vanderbilt University, with University of Iowa, with Rochester Institute of Technology, with Virginia Tech, and a few others. So we partner very, very smartly with the universities to try to get those launches to keep our hobby in space. So our vision has become partnering with these educational groups to get our subsidy to launch into space. And basically the sticker price to build one of those CubeSats can be anywhere from about $75K to $150K, depending upon what we put into it. And we have to raise that for ourselves. And then the subsidized launch that's $120,000, we get that from, basically from NASA. And NASA likes us because over 90% of first-time CubeSat launches fail. The idea of the CubeSat was to teach you integration, was to teach you how to build a program. It's not to make an operational satellite. Now, if you go through that process and your satellite operates, you're king of the heap. So we have 3 satellites in orbit right now that all work. And AO-85 is a little deaf, but it does work.
Is there some side benefit that happens in industry that you guys help with? Or
Not in industry, because we're a nonprofit, but in the university communities, we're highly, highly respected.
Talk about the technology.
The technology is trade-offs. A lot of this is cost, commercial off-the-shelf stuff. But right now we're building a technology demonstrator that I could tell you about, but I'd have to kill you. So that sort of thing. The new technology for being able to point. So education is becoming critical for us to get launches. And that's our whole CubeSat strategy. So our goal is an Oscar in every CubeSat. Oscar is orbital satellite carrying amateur radio.
I was wondering what that meant.
And see, you never know what you'll learn. So there's our CubeSat. Go ahead and hit it again. We'll buzz through these. So what does it do for hams? Basically, we replaced AO-51, which was really popular. It's a CubeSat. First ham CubeSat was AO-73. We did the first one in the US with AO-85. Telemetry beacon, command receiver on UHF, simple internal housekeeping unit, and costs us with launch about $150,000 for AMSAT. And the A is for the Canadians. So AO-85, antenna delaminated. So we tried to glue it back together with some conductive epoxy. There, just as with any spacecraft, it has its own personality. And the spacecraft builders also have their own personality. Our Vice President of Engineering claims that, oh, it just must have not been a good conductive joint. Our guy who did all the programming for it says, oh no, it's broke. So it's one of the two, but basically you need about 10 watts to get into the antenna. And the operations guys, they're on the broke side of things because they just boost the power and they get in on it. It's got a great, great transmitter. You can hear it on your mobile rig driving around. I keep it tuned on my 710 and I can hear it when it comes over and makes a pass. I hear all the downlink. But getting into it's a little bit of a challenge. So uplink, 735, 172, downlink, 145.98. And we have a Vanderbilt radiation experiment on it and some MEMS gyros expected on it. And that one had a 19-year orbital life. So hopefully the way the batteries will keep working, they are NiCads. So hopefully it'll last 10 years or more. That's what it looks like. So right before we launched it, those are some of the covers that we put on it. for the solar panels, and this is a challenge coin. So I will let you know, if you donate $100 to AMSAT, you get a challenge coin. Hit the next one. Our next one's AO91. This was launched, November of last year. It's almost a year old. Out of Vandenberg. Again, UHF up, VHF down. And it was a partnership with Vanderbilt on a radiation experiment. And that's what it looks like. And we use telemetry that is called data under voice, DUV. So everything under 300 hertz is actually tone data that comes down. And we always get complaints from the operators, is like, what is that train noise? Because it's a low bass noise. Well, that's the data. So one man's noise is another man's data. And you have to remember that with using all of the Fox series satellites. So AO92, this one we did our own experiment on. We call it the L-band downshifter. Basically, we use 1.2 gigahertz to communicate on the uplink, and it comes down on UHF, or we can switch that to VHF for the downlink. So, or it comes down on VHF, I'm sorry. We can change either UHF to L-band on the uplink. I'll say that again. 1.2 or UHF up, VHF down on both. And we did that. That was our own experiment we did, and with one Clift, when it gets launched before the end of the year, it'll have that same feature as well. And this one also has a camera on it. And it had a radiation experiment, much like the Van Allen radiation belt experiments the University of Iowa built on the Vanguard experiments that went up in the late 50s. And that was called Herky. And Herky is the hawk for the University of Iowa, the mascot. So the Iowa Hawkeyes, Herky the Hawk, they went all down with it, and that'll be some of the telemetry that you hear on that particular satellite. We tried to turn this on the other day. This was launched out of India in January, and we watched the rocket launch. And India had a problem with the previous rocket. The fairing on the front of the rocket never separated. So all 30 satellites went up into orbit in the fairing, and none of them ever deployed. So during the launch, the Indian Mission Control, they're watching all of these very serious sort of folks looking at everything, and when the fairing separated, the whole place erupted in cheers. You would have thought that that was the biggest thing. Some mundane part about the space launch was the biggest thing, because it worked this time. And I can tell you there were some cheers in the U.S. because we were glad that it separated too.
You always get free rides, or you got to pay?
No, we paid for the one on the Indian rocket and for the one Clift.
How do you stabilize the little cube? Because I imagine you don't want it tumbling.
Passively and poorly. The golf series, we're doing attitude, determination, and control, and I can't explain anything more than that. You can talk to me later and I can point you in some directions of that, but that's basically a miniaturization of what you do on really big satellites.
And you might be benefiting from that relationship with the gyros.
We're benefiting with some relationships with some corporations in doing that, yes. So that's the Fox series. We use what's passive. So what we do is we use a bar magnet and a set of hysteresis rods. So there's 3 different planes. There's your X, Y, and Z plane, and plus or minus each way. And what you want is to impart a little spin so that the satellite rotates, so it's not 300 degrees difference on one side of a 10 centimeter cube than on the other. And that evenly heats the satellites and uses the solar panels efficiently. And the bar magnet keeps the antennas that are on the Z-axis pointed at the Earth, the magnetic poles. And it is supposed to have 2 revolutions per orbit. Well, I think we got smarter than ourselves, because one of the things we did is we offset the solar panels. Think of the way that the light actually hits the solar panel. It is a particle and a photon. It does have some small mass, so it doesn't hit straight. And on the solar panel, that engages the wobble that the magnet is supposed to take out. Well, we find that the satellite tends to tumble a little bit more than expected, and we think that by offsetting the solar panels, that's what did it. And I had a long conversation with Bob Twiggs, who wrote the CubeSat standards, and that's what he thinks that's doing it, is solar pressure. We thought it was actually the magnet. We thought we had figured something new out, but no, actually what we did was we goofed ourselves up. And we talked to the AMSAT UK guys. Their satellite does the same thing. Their solar panels are offset. The other solar panels that are not offset don't seem to have that problem. So we've discovered a few things. You know, even though we've been doing this for 50 years, you still learn things when you size up and size down components. And this is our first go around with CubeSat, so that's one thing I think we've learned is don't offset the solar panels. So our next foray is we use the adaptive control mechanisms that I can't talk about to be able to stabilize the spacecraft. So 1D also has the camera on it. We tried to image the hurricane here these last few days. If you collected telemetry, please make sure that that gets into the data warehouse, because we actually stitch the pictures together from a lot of the telemetry that comes down. So there's an image. That's what a VGA camera looks like from orbit at about 500 kilometers. There's the antenna and the fishing line. And I think I have another one. That is Nantucket Island. And one of the things we had to do as AMSAT was we had to get an NOAA license for visual images. And you would say, well, what does the weather people, why do they care about you having an imager? They don't. But they're the clearinghouse for the three-letter agencies who do. So we have a license through the NOAA for our imagers. They come out and inspected our command stations, including the guinea pig cage that was next to the command station, and made sure that there was at least a burglar alarm on the house. So even as hams, we have to go through the same sort of regulations that we would as if we were SpaceX or General Dynamics or anybody like that, because of the images. And we had to actually do the calculations to determine how close something would have to be to resolve it at VGA resolution. So if I have a spy satellite go past about 30 feet away, I can image it. So warning. Okay, next one. We also took over FalconSat 3 last year, and that is a store and forward, or like a packet satellite that the Air Force Academy built. Its tertiary mission, so its third mission, was amateur radio. So they turned it over to us, and we now operate that. And that's been a great satellite. You can see that it uses WISP, a 1995 technology. So everybody should be current on that. And you just don't use it with Windows 10. I think you have to run XP or something like that. I run Linux, so that gets me in all kinds of trouble. Okay, next one. So Fox 1 Cliff will be the next one that we launch. It'll also have a camera on it. It'll go out of Vandenberg in late 2018. The one thing you can count on with spacecraft launches is they will slip. And then we have Fox 1E. Again, this will go up on a Pegasus. This is a Virgin Galactic, I think what they call them now. Richard Branson's 747 with a Pegasus rocket strapped on the bottom. And that will be one that we have a linear transponder on. And again, that one is going to go by the end of the year.
That's Northrop Grumman now.
Is it Northrop Grumman?
Yeah, yeah.
I can't keep up.
Yeah, Orbital ATX combined with ATK, and then got bought by Northrop Grumman. So now they're NGIS.
Yes. Did Branson buy them? Oh, the Pegasus. The Pegasus, yes.
Yeah, this is Pegasus. Yeah, Branson's doing the other one, the launcher one as well as.
Yeah, he's doing the actual aircraft, and I think Orbital ATK is the rocket.
Okay, well, the Orbital ATK runs their own L-1011
Right.
aircraft, and then they've got the Pegasus rocket. And then Branson's doing his own version of a Pegasus that's supposed to be cheaper, so.
Yeah, and we're on the first flight
Okay,
for
so
that.
you're going up on Launcher 1 then?
Yes, we're going up on Launcher 1, so how do we get a subsidized launch? You take your chances.
Yeah.
We're the first, and sometimes the first is suboceanic. So, go ahead and hit the next one, please. So here's basically our block diagram of it. This is our magnetic attitude control that I was explaining about the bar magnet and the hysteresis rods. That's the bar magnet. The hysteresis rods are on the mass, on the battery, and the hysteresis rods elongate and contract depending upon the temperature, and that's supposed to take the wobble out. And apparently that works really good, but the bar magnet probably is too weak, or it's too weak to handle the offset solar panels. You can see the different cards. That's a lot, 10 pounds into a 1 pound box. Go ahead and hit the next one. That's what the solar panels look like. There's 6 solar panels. Next one, we'll buzz through this real fast. This is in case you're a hardware geek. Basically, there's the test of all the solar panels. Next one, power supply cards there. The power bus powers everything on a spacecraft. That is the maximum power point tracker. So one of the things we did is we partnered with a university. They built a circuit to optimize the power coming out of all of the solar panels. So think about solar panels on Earth. They track the sun, right? How do they do that? Well, they have a maximum power point tracker. They sort of move the panel around a little bit to keep the highest output on the solar panel. Same thing in reverse, it's done with keeping the voltage hot on the spacecraft instead of moving the solar panels. Because the solar panels are moving. You don't have any choice in that, it's spinning. So, same sort of technology that applies both in space as on the Earth. Battery card, NiCad batteries, hit it again. 70 centimeter antenna, that's the short one. Next one to the receiver, and there's the receiver board. You can see that these are conformal coated. We did learn something here. You see the 3M tape on the connectors. We found that when we conformal coated all of the boards, that the connector assemblies were so close that it coated the connectors. So we tried to come up with a new connector design on our next version of spacecraft to keep that from happening. And basically we had to chip off all the coating, which kind of defeats the purpose for the connector. Transmitter card, 2-meter antenna. And there's a transmitter card. Very, very simple. We do put these in sort of RF enclosures, like you remember from your old crystal radio sets and your tube sets. A nice resonant enclosure. That's more for temperature than it is for keeping resonance in a cavity. Basically the internal housekeeping card. And then we have the radio cards. That all goes in with the telemetry to the housekeeping card. We keep the housekeeping card powered up. Go to the next one, please. And the battery card. So we can't get NiCad batteries anymore. We've used these batteries for 25 years. They quit making them. We bought the last ones up. That's why we can't build any more Foxes. So we don't have the batteries for it. And we were worried about them freezing. So we wrapped them with wire to heat them up. We have yet to turn the heaters on any spacecraft. They just don't need it. In fact, they're operating 10 degrees hotter than we thought they would. So we haven't had to do any of that. Maybe that's something of our orbit, but we have the heaters there in case we ever need them. So we've gotten good luck out of these NiCads. That's why we still use them. And we can't get them anymore, so now we're going to lithium ion. And no, not the type that explodes. So here's our battery heater prototype test. You can see we measure everything with thermocouples, very small size, very compact. And then the science payloads, we call this space for rent. That's where the universities would give them, you have to build it to this size, here's your voltage requirements, and they give us an experiment. There's the Vanderbilt experiment card. You can see it's pretty much CubeSat size. And then the prototype, always love this, serial number 1. Yes, that one got launched. So the magnetic attitude control, that's the bar magnet. So we have a passive system, aligns the z-axis with the field, like I said, and the hysteresis rods dampen the effect. So we also had MEMS gyros on these cars. So MEMS gyros in opposite sort of angles, so that we could measure electronically what was happening with it instead of trying to determine what the spacecraft was doing with the voltages off the solar panel. And that lets us know that it was tipping. The other problem we found in this was spacecraft are purged with nitrogen. MEMS gyros don't like nitrogen. So when you purge it, you lose all your calibration. So we ended up launching this, and all the MEMS gyros had no calibration, and we had to figure out a method to try to calibrate that. And I don't think we were ever successful, but that's my opinion. What do I know? I'm just the president. So then we had a JPEG camera from Virginia Tech. We had to get the license from the NOAA. And we are a private remote sensing satellite. And we, another amateur radio and AMSAT FIRST, we're the first satellite that's been licensed like that. And yes, they come out and inspect us every year. So that's where all the different boards go. You can see the top half of the spacecraft is basically dedicated to those educational groups that get us that type of launch. Here's the camera board. And I talk about zombie mode. Remember I talked about AO7. So here's what didn't happen with the Fox series. So we were designing the satellite at the bar, and we were drinking beer, and we came up with zombie mode. And at that point, we were going to have 4 satellites. And we figured that if we sent a CW message that said, brains, that every 24 hours that it was in zombie mode, we would add an A. So the longer it was in zombie mode, the more it would say, brains. And then we had to figure out how to determine which satellite was going to be up there. So we got the 3-letter codes from Columbus, Tallahassee. I don't know if you've ever seen the movie Zombieland, but the airport codes from the cities that the 4 main characters were at, and that was going to be determined on the spacecraft. And we never integrated that. So one of my favorite stories, that's what happens when you join AMSAT. You come up with all these crazy ideas, and sometimes it gets integrated and sometimes it doesn't. But I'd like to know if it was in zombie mode, I really would. So Golf, greater orbit, larger footprint. So our satellite footprint, remember I said the higher orbit you are, the better distance you can communicate with. 3U and beyond, this is our next satellite that we're building. We have attitude stabilization. We are building the satellite right now. I have a good partnership with a company that is helping us build the attitude determination and control and providing us the new power system. And it's going to be 3U. So we also highly elliptical orbit, which means it's like an AO7 orbit. So up to about 15,000 kilometers is where we'll end up. Golf T, which is the demonstrator, will end up about 600 kilometers. Golf 1 will be up at 1,500 kilometers, and we're trying to partner with a high school for an imager on that particular one. So we try to push this down. 1U and 3U, we're pushing down into the high schools. The universities are already building 3U and 6U, and that's our next step. So we're trying to figure out how we can take steps to get to higher orbits. And hopefully by the time we get to the hotel program, we'll be there. So we'll also have partnerships with Vanderbilt. So our partnerships with Vanderbilt were very, very successful, and they're on board again. And so there's Golf T, radiation tolerance. Every time you go to higher orbits, more radiation, which means you add more lead, which means you add more weight, which means you have less room for electronics. So always a challenge in a shoebox. And Golf 1, you can see 2020, that's where we're going. That is the 1,500 kilometer, should have 5 and 10 gigahertz software-defined radio transponders on that one. So look forward to new modes. And like I said, we're partnering with Albuquerque Public School and Virginia Tech to put a weather camera on that, or a imager. And that one will have deorbit capability. No, I'm not sure I can explain what that means at this point, but no rockets at this point. If you think about this, where we're going, the next step is really strap on a rocket. So when we go to launch something that has a rocket on it, it pretty much has to be bomb-proof, because that's what a rocket engine with its gas is basically an explosive element. Even if it's just pressurized air, it has to be a titanium pressure chamber that fits in that small CubeSat form factor. So very, very expensive to do this. Nobody with $1 billion satellite is going to let you strap a bomb as a secondary payload onto their rocket. There is just not going to happen. So you have to go through lots and lots of testing, lots and lots of certification to be able to make this happen. So that's what it's going to take to get to HEO and beyond. So I talked about beyond. 12U, that's a lot of room, a lot of mass. That's all up in microsat size. Right now, NASA finally in April launched a 3U interplanetary satellite to Mars. So even NASA is only at the 3U size. But we already have the plans and specifications and form factors for 6 and 12U. Very, very cheap. You're talking about spending less than $1 million for a big satellite that used to cost a couple $1 million. So we also do something else. We play around with this. This is the International Space Station. So we have a radio on it that's broke that we're trying to replace. We've done 1,000 school contacts. And basically we have ham TV on it, which means at 2.4 gig we can download video. So we're working right now on the interoperable radio system. Basically this is a power supply with some Kenwood D710s on it. And there's the D710. Kenwood donated them to us. The only modifications Kenwood made was they put a fan on the back, big fan, and the default for the radio is now our own series of program frequencies, which makes them both astronaut and cosmonaut proof. You've never hit the defaults, the reset defaults on a radio, right? That you have 1,000 memories programmed in. So now it defaults to the memories we want, not the factory. So it happens, you know. This is research. This is a ham shack in space. And if you've ever actually seen the videos of what that looks like, it looks worse than your closet. So next one. So there's basically the camera system, ham video system, the Kenwoods, the power supply. We had to build the power supply. To get the astronauts to use this, there's a secret. We put USB recharger ports on it. They have all their iPads and all that kind of stuff. They have no way to recharge them other than plugging it in. All of the modules in the ISS are different voltages. So this adapts to all the different voltages. So the multi-voltage power supply, lots of thermal overloads, you know, anything that could catch on fire they worry about. So we actually have silicon insulation wire that we use for this. So that's what a lot of the power supply looks like. You can see right here. This is the multi-voltage, all the different tests. We built one of these and had it tested. It is the first piece of space hardware that has passed both the US test and the Russian test. So again, more test equipment that you can shake a stick at. This is one of the guys' labs in San Diego. I think this is Kerry Banky's lab. So right here, radio on top. Here's all the different connectors, the different power supply lights that come on, the different outputs. And next one, and there you can see the back in the connectors. So here is DC in, the other is out, one side or the other. And there's the flight units, that's what it looks like. I'm trying to find, oh yeah, there's a bunch of USB ports right there. Next one. So next one, again, more testing. USB ports right there, you can see them. And again, that's the 5 slides on it. This is the prototype. It's made to resemble the flight unit, but this is one we can tear up and destroy. So we're doing a fundraiser for this. We need to raise, next one if you would please. Here's all the different units we have. We have flight backups, Russian backups, training, No wonder we need 10 of them, we got to train on them. And we're doing a fundraiser, we're trying to raise $150,000 in the next year and a half through fundraiser. So if it's a nickel, give. Basically, if you give big money, you get prizes. So there's the first different ones. So if you'd like to have your name and call sign on the website, some of these, I think, there it is, name, call sign on the power supply on the ISS, $2,500 tax deductible. So we do experimentation. Go ahead. So Marconi or Macronista, this is an experiment on the ISS. This is basically a Lime SDR floating around the ISS, and this is flying right now. So there it is. That's what it looks like. We throw CubeSats overboard. They last about 60 days. So we like long term, so we don't launch. AMSAT tends not to launch from the ISS. And of course, we need volunteers and donors to make all of this happen. So here's different things. If you have mechanical, electrical engineering, we want you. If you like to do education, we want you. If you want to mentor groups, if you want to do ground stations. Basically, the dream's still going on. 21 years on the ISS and another 10 years to go. And then comes Deep Space Gateway, a lunar at the L5 point, the range point out between the Earth and the Moon, a stopover for astronauts on the way to the Moon. It will have amateur radio on that spacecraft. So different mission opportunities. We got golf, we got HEO, CubeSat simulators for education. And want to learn more, go to AMSAT.org. Don't ask me. I'm just the big dummy that's present. I think that's it. Oh, you get the AMSAT Journal if you join. Our monthly or bi-monthly magazine, and then the next one. This is different resources. We have bulletin board, KEPs, educator boards, that sort of thing. And I think that's it. One of these says, if you have any more questions, call Martha. I think that's it. So that's it. Thank you very much.